Good evening, all. Welcome to the problem solving session for the course Matlab Programming for Numerical Computation. Let's wait for like few more minutes to see if there are more students to join, and then we'll start. So right now it's 6, we'll start by like 6:02 or 6:03. Okay. So it's just whoever is there in the meeting, please stay. We shall start soon.
Good evening, ma'am.
Yeah, good evening.
Ma'am, last week assignment, no, that Newman conditions, boundary condition problem.
Yeah,
Uh, can you explain that, ma'am, assignment problem?
the particular assignment problem. Uh,
Yes, ma'am. We have done, but we got that in the assignment that answers were wrong. So I
okay.
did not understand where we have done wrong. Can I put it
Yeah,
my whatever I have done the MATLAB code in the chat, or you will show, ma'am?
yeah, okay. You can put it in the chat. Yeah.
Okay, ma'am.
By the time, let me just go and read the question and come back. Okay. Do you know the question number?
Ma'am, second question, ma'am.
Yeah, okay, okay. Just give me some minutes.
ಏನು ಇಲ್ಲಿ
Okay, do one thing, just put the answer, put your code in chat box. I shall go through it and yeah. Just a second. In this question, where is the boundary condition? Where have you given the boundary condition? Oh, okay. Just give me a second. So, who asked me this question? What was your name?
Ma'am,
Vishalakshmi.
myself, Vishalakshi, ma'am.
Yeah. So, Vishalakshmi, I don't know if I'm sharing it right. Just a second. So, this is the question, right? So, here the condition, this is at one end of the road, that is at z equal to 1, and this is at z equal to, sorry, z equal to 0, and this is at z equal to 1, right?
Yes, ma'am.
So, did you see the last week's like basically a presentation last week? So here I had told here we have a condition for x is equal to 0, and here the condition is for x dash. Okay, at the other
Yes.
end of the road.
Yes, ma'am.
Okay, so the main thing is I want to make sure that you have coded this right. That the boundary condition, the second boundary condition will be at the okay, I think I have to show you the MATLAB also. The boundary condition, the way you have coded it might be a problem. So
Ma'am,
let
I've posted here whatever I have done the code. Where I've done wrong, ma'am? In the function, no, in the
not in the
boundary condition.
function.
In the boundary conditions, ma'am. Here,
Could
I
be,
think
could
I
be. Usually, just a second. I have to look at my MATLAB also. Where was your boundary condition? Prop to fun is your boundary condition.
ma'am.
Which is your boundary condition function?
Ma'am, here the last one I put no function residue
Okay.
is equal to
Yeah,
prop.
yeah, 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 yeah. So that there could be a problem. So I show you MATLAB. See, y has two variables as we have discussed earlier. So I think I need to.
Ma'am, I think I have to give in the residue 2 comma 1 y1 comma 2 no.
Yes, yes, yeah. The
Yeah,
index
yeah.
has to be correct.
Yes. I just executed. I got the correct answer.
Yeah. You
Okay, ma'am.
understood
Thank
why?
you.
Because
Why?
the two one is the index for the starting of your road and two is the index for your end of the road.
Okay.
Yeah. Okay. So
Thank
shall
you,
we?
ma'am.
Yeah, sure. So shall we start with today's session? So this week we'll be discussing about PDE. So far what we discussed is we had like ODE solvers. So that is ODE initial value problem and ODE boundary value problems. This week we'll be discussing ODE solvers. So just give me a second. I hope you can hear me. So far what we had is we only had a single dependent variable. Okay, so either it was time or position. So for example, you had something like this, the road conductions here problem that you see. Here the dependent variable is temperature and the independent variable is position, and you have a function here given. So here you can see it is written as d by d, that is dt by d is it. But what if our function has more than one independent variable? That is, if you have two or more independent variable, what we get is a PDE, partial differential equation. So this is an example of our partial differential equation. Here you can see your temperature is varying with respect to time and position. So there are two independent variables, that is time and position. So this is called as a transient condition. Transient means whatever that is changing with respect to time. Steady state means it is constant with respect to time. Okay. So here what you can do is, if you're telling that, okay, if you want to convert this road conduction problem to steady state, we assume that the dou T by that is change with respect to temperature is equal to 0. That is, this will go to 0. Then what do you get? You can just rearrange it, taking the beta to the other side. And if you bring this alpha to the denominator, it becomes beta by alpha. And you can call this parameter to be gamma. So that will be equivalent to this. Okay, the road conduction problem steady state. Okay, is that understood how to convert a transient problem to steady state problem? Basically, when you mean steady state is that your system is not changing with respect to time. So you can write dou T by this thing. That is, change in temperature with respect to time is equal to 0. Now moving forward, we have like a conduction in a, so this is independent variable is time and position. Okay, so here in this case, you have like two position coordinates. So here we have a plate here like this, with this, which has, let us assume this to be the x direction and this to be the z direction. So you have heat transfer that is happening in all the directions. Okay, in that case, what we have is, this is a conduction in a plate. The independent variables are the two position coordinates, that is the x and z coordinates. So we will be trying to solve PDEs in this week. So first let us look at second order PDE. Second order PDE means when we have the square term. Okay, so that is called as a second order PDE. This classification is only true for second order PDE. We're not talking about first order PDEs, okay, in this particular classification. So be careful. So the second order PDE itself, it has like different behavior. Okay, so based on the behavior, you can characterize your second order PDE into three categories. That is elliptic, parabolic, and hyperbolic. How do you identify just looking at your equation if the system is going to behave elliptic, parabolic, or hyperbolic? So the thing is, we have to write the equation in this form. Okay, we have to write the equation in such a way that your first independent variable square comes here. This is your this is a mixed term. Your second independent variable, and this is your first order terms. Okay, write it in such a way. Now you have to take A, which is the coefficient of your second order term, B, which is a coefficient of your mixed term, and C, which is a coefficient of your next second order term. So this is only applicable for second order ODE. First order ODE, we are not talking about it right now. So once you've got these parameters A, B, and C, we have to just calculate B square minus 4AC. If it is less than 0, then we say that the system is elliptic. If it is equal to 0, then we say the system is parabolic. If it is greater than 0, we say the system is hyperbolic. And first order PDEs, that is, if you don't have any of these three terms, if you don't have these three terms and only this terms, it's a first order PDE. You don't have the square terms there, right? So the first order PDEs are always hyperbolic in nature. Okay. So this is the classification. Now let us look some of the examples we have. So this is a transient road conduction. So here you have the dou T by dou T and plus alpha dou square T by dou Z square minus beta T minus T alpha. So basically you need terms for this term, that is Z square. Here you need a coefficient. So that coefficient will be A, and the coefficient of mixed term, that will be B, and the coefficient of the other term, so we don't have a, so if the coefficient of the second term, probably dt by dt square, the coefficient will be C. Okay, here in our case, do we have any of these terms? Okay, so let's assume that is, just a second. Yeah, so we don't have a mixed term. So what we can say is, in this condition, B is equal to 0. Okay, I can say either A is equal to, since both are, I can interchange A and C. Okay, that is also not a problem. So in this case, let's go with what I started. Okay, let's we say that A is equal to 1, B is equal to 0, and C is also equal to 0. Okay, Now what happened? B square minus 4AC is what? That is 0 minus 4. Sorry, A is equal to 1, right? Alpha, sorry. Okay. 4 multiplied by 0. So the answer is, net answer is 0. So it is parabolic in nature. Even if I exchange this A and C, I'm going to get the same thing. Okay, here in this PPT right now I have written A equal to 0, B equal to 0, and C equal to minus alpha. And when you multiply the entire thing, you are going to get again 0. So it is parabolic in nature. So basically in this category, we have transient problems. Basically the systems which have dou by dou t terms, usually cohorts in this category. That is diffusion problems, conduction problems, etc. Okay. Now let us talk about this conduction in a plate. In conduction in a plate, you have like the two second order terms. Okay. So in this case, you can say A is equal to 1, the coefficient. B is equal to 0 because you don't have a mixed term. And C again it is equal to 1. So what is B square minus 4AC? This is equal to 0 minus 4 multiplied by 1 multiplied by 1, that is equal to minus 4, which is less than 0. And hence the system is elliptic in nature. So these category usually involves boundary value problems in both directions. That is, uh, we have two position coordinates. And one more thing, if you need to solve this such a question, okay, if you want to solve such a question like this, what all conditions do you need? You know, it is first order in time and second order in terms of position. So to solve it, you need one initial condition, one condition for time, and two boundary conditions in terms of position. Okay, then only you can solve this. In this case, what you need? You need two boundary conditions in terms of x and two boundary condition in terms of z. Okay, this is x, sorry. So this is what you need. So hyperbolic PDEs are usually wave functions. Okay, we're not discussing about that this time. So let us move forward. If you have any doubts, please to stop me and ask, okay? So these are the examples. We have here the Laplace equation, that is basically the conduction on a plate, which is elliptic in nature. You have a wave equation, which is hyperbolic in nature. So this you can see it is second order in terms of time also. Okay, this term. Now it is a heat equation. This is a transient rod conduction equation which we had. In that, the system is parabolic in nature. Okay. Now going back, so we have like PDEs in like broad range of categories, and there is no single way in which you can solve all the kind of PDEs. Okay, one solution doesn't fit all kind of PDEs. There are PDEs in space which are elliptic in nature. That is only x and z axis are there. Then there are PDEs in time and space. These are the transient conditions. So that is either parabolic or hyperbolic in nature. Now there are different ways in which you can solve this problem. In our class, we'll be discussing these two methods. Okay, this is finite difference. That is, if you have a road, you're gonna divide into finite or like finite, what you say, intervals. Okay, so if you have n intervals, you have like n plus 1 values here. Okay, this we have already seen in our previous classes. So this is one way to do it. This is finite difference. The other one is method of lines. And method of lines we solve in PDEs which are in time and space. Okay, that is this kind of PDEs. That is either parabolic or hyperbolic PDEs. So let's start. So the first thing we'll be using method of lines. Okay, so do I have a, yeah. So this is a question that we have. That is a transient heat rod conduction equation. That is, your temperature is changing with respect to time. So you have the dou t, the change in temperature with respect to time, equal to alpha square dou square t by dou x square minus beta t minus ta. So here what happens is, the idea is we will convert this portion, okay, using our finite difference. And then you will have a set of ODEs to solve. So this is basically you're converting your PDE into multiple ODEs. Okay, so this is the idea about what we'll be looking at. So before starting, let us look what all conditions are given. We are given the constant, the alpha parameter and beta parameter is given to you. And it said that the rod is held 100 degrees Celsius at one end, and the other end of the rod is 25 degrees Celsius at the other end. And it is also changing with respect to time. So initially the entire rod is at 25 degrees. So what happens is you have a rod like this. Okay. So at t equal to 0, the rod it has 25 degrees Celsius. Then you are providing a heat source here, and this is maintained at 100 degrees Celsius, and this is maintained at 25 degrees Celsius. So we need to know as time progresses, what will be the temperature of the rod, and also with respect to position. So this point at from t equal to 0 to, let us assume t equal to maybe 5 minutes. Okay, I'm just taking a particular value. From t equal to 0 to t equal to 5 minutes, we have to see how the temperature is varying at this end of the rod. Okay, and this portion. So here we are trying to calculate the change in behavior of the rod, both with respect to position and with respect to time. So let's try to do that. So this is the equation that you have. Okay, this is the equation that you have. We need to take this term into finite difference formula. So how do you do that? So for doing that, you know, this d square t by dx square term in finite difference, in central differentiation formula, if you write it, you get it as ti plus 1 minus 2 ti plus ti minus 1 divided by x square. That is, the whole rod is divided into n intervals. So you have n plus 1 data points. And for a particular interval i, you can take the value at I plus 1 and I minus 1. You will be able to calculate what is the dt by d square t by dx square at I. Okay, at the ith position, you can calculate here d square t by dx square using this finite difference. Now let us put this formula back into the equation. So the whole rod we are dividing into fine entries. Here you know the temperature is 100 degrees Celsius, and here you know the temperature is 25 degrees Celsius. Okay, so we need to know how the temperature is behaving at an intermediate point I. So at that point, dti by dt can be written as alpha times a finite difference minus beta ti minus t alpha. Okay, basically we have written the same equation for a particular interval. Now we know the starting temperature is 100 and the last temperature is 25. You understand why there is n plus 1? So if you're dividing a rod by n intervals, there will be n plus 1 data points. So this will be 1. So how many intervals have I divided in this? 1, 2, 3, 4, 5, 6. So 6 intervals. That will be 1, 2, 3, 4, 5, 6, 7 data points. Okay. So if there is n intervals, I will have n plus 1 data points. Okay. So my first interval data point value is 100 and the tn plus 1 is 25. What I need to find is from t equal to 2 to t equal to n. Okay, so this is what I need to find out. Rest of the things are given to me. I only need to solve for t equal to 2 to t equal to n. What we will solve, so once we have written this in the finite difference format, you can see that every ti, so t2, you will have an equation like dt2 by dt, then you will have dt3 by dt. So go on, you will be having dtn divided by dt because already n plus 1 is given to you. So what is this? You will have a set of ODEs. A multiple ODEs. Multiple ODEs also you can solve using ODE 45, right? So this is what we'll be trying to do. Just give me a second. Let me share Matlab. So this is the code that has been shared in the recorded lectures. We'll go through it once again. So first to begin, we are dividing the whole interval into 10. So there are 10 intervals. And I need to have an initial temperature range. So my initial temperature T vector, I'm calling it as T0, which will have like 1 to how many? 1 to 11 data points, right? And I'm telling the first data point T11 is equal to, it's a column vector. So that is why you can see this is 1, 1, it's a column vector. My first entry is 100. So T011 is equal to 100. And my last entry, that is T0 n plus 1. n is equal to 10, so n plus 1 is equal to 11. So that one is equal to 25. And in between, that is from 2 to n, I am telling the initial temperature it is being given to you in the question, it is 25, right? At the beginning of your experiment, your temperature at every row, every point, you're talking it to be 25. So this I take as the initial value, 25, 25, so on. So now I've got the T0, the initial thing. Why do I need the initial thing? So you remember, this is how the ODE solver works. You have the keyword, you have the function that gives you the equation for dt by dy. Okay, you need the equation for this that is given by this function. You have the t-span, what all time interval you are solving the ODE for, and you need the initial guess, right? So my t-span I'm taking from 0 to 20 seconds. Okay, and my y0, that is the initial, what I need not solve for this and this, it's already given to me, so I only have to solve for this part. That is t0, it will be basically 2 to n. Okay, I don't have to worry about 1 and n plus 1 because that has been already solved. So I only solve for 2 to n. So that is my initial value y0. That is t0's 2 to n. Is this clear? So that will be your y0 here. Now let us look at this rod conduction. Okay, so going to that. So this is your rod conduction. Yeah. So here in the rod conduction, you can see it will take in time and y value. And what is y value? Y value will be basically having T2 to Tn. T1 and Tn plus 1 is not there. Okay. Now these are the values that are given to in the question. T alpha or Ta is equal to 25. Alpha is equal to 0.025. Beta is equal to 0.1. Okay. Now how many intervals do you have? So how many intervals this will have? How many entries? Just a second. Sorry, here this y is your total y. Okay. So it has like, sorry, here your y is your total y. So this has basically T1 to Tn, right? Just a second. Mm. Oh, sorry, I was correct. So this y has only T2 to Tn. So basically earlier you had n plus 1 values. Now you have like n plus 1 minus 2, which is n minus 1 values. So this is the length of your y vector. Okay, n minus 1 values. So from that you need to identify what is your length, total intervals. So for that you can just take what is n intervals. N is equal to length of y plus 1. You have to take the 1 to the other side. So that is what we do here, length of y plus 1. And your first value is 100. The next value is given by this y. Okay, 2 to n, it will be this T2 to Tn. And next is last value is Ta. And what is your interval size? 1 divided by n, basically 1 divided by the number of intervals. So now moving forward, what we do is we have to write the ODE equation. That is dti by di has to be by dt has to be written. Okay. So for that, what do you do? First, I am initializing this column vector to be all zeros. It will have all zeros. Now I'm not bothered about what is happening to my first entry. So here n plus 1 means it will have dt1 to sorry dt dt2 to dt up to what will be here dt n plus 1 divided by dt. I'm not bothered about this. I'm not bothered about this. So I'm only changing 2 to n. Basically, only this function I'm bothered. So what will be that function? That will be written alpha by x square. This is the central difference equation. Ti plus 1 minus 2 ti plus ti minus 1 plus beta times ti minus t alpha. Whatever we saw in the PPT, that equation will be written here. And now what will happen? For the entire dt, I'm only giving this as the output. That is from t2 to tn. So the entire d by dt column vector, I only take from the second to the nth entry. Is this clear? Okay. If you don't understand this portion, there's the n part. Okay. You don't have to make it all complicated and all. You can directly give that as an input. Okay. You can directly give n as an input here also. That is also completely fine. Okay. So understand that though my vector, now the question might arise that, okay, since I'm only solving for this 2 to n, why do I need this 125 in this value? That is because if you're trying to solve for t2, you know that in the finite difference equation, you need t1, right? Sorry, you need t1. Okay, so that is why we have written this 100 in the equation. Okay, so you get t1 from here. And when you're solving for the tn, you need tn plus 1 also, right? According to the finite difference equation. So that is why we are giving that also in the problem. So now we have got all the ODEs. You have got a set of ODEs for 2 to n. So that will be given as an output to back into this rod, this code. So that will be given here. Okay. Now, as usual, we'll run this ODE equation. And what you will be getting? You will be getting T sol. And what will be there in Y sol? In Y sol, you will have T2 behavior, T3 behavior up to Tn behavior with respect to time. So we'll look at that. Let me just run the code. This is how the plot looks. We'll come to that plot later. Okay. So let us look how the Y sol looks. Okay. This is your Y sol. And this is your T sol. So your T sol is varying from 0 to 20. Just a second. Yeah. 0 to 20. And you can see Y sol. How many intervals we had? We had like 10 intervals, which means 11 data points. Out of 11 data points, how many we are only solving for the mid one. So 11 minus 2, that is 9 entries we'll have. So you can see there is 9 columns here. Okay. If you see the 9 columns, okay, 9 columns are there. See, 9 columns are there. And if you see the 9 columns at t equal to 0, so the first row is for t equal to 0, corresponding to t sol's first entry. Okay, T sol's first entry. You can see every portion, every point is starting with 25 degrees Celsius. But as time progresses as per T sol, you can see the temperature is changing. And the change is not the same for 2 points. Okay, it is here 26.23. Here the temperature was 25.03. Now, if I want to plot how the behavior is, what I can do is, so if I want to see how the behavior is, what I can do is here, T sol versus Y sol, what will happen is for every temperature, for every particular time, I'll see. So the plot is like this. Okay. So here the time is changing and every line corresponds to one particular position of the road. Okay. So this you can see. Okay. So this is as time progressing from 0 to 20. And this each line corresponds to one particular position of the road. Okay. So here you can see it is coming close to 100. Okay. So here we have 100. Here we have 20. This is the end of the road, which is close to 100 degrees Celsius. That is this point. Okay. That is this point. And now this point is here. Okay. So you can see everything started from 25 degrees Celsius. But the one which was close to 100 degrees Celsius, what happened? Its temperature also started rising and became close to 100. And here you can see, here we have a one end of the road at 25 degrees Celsius. One end of the road of 25 degrees Celsius and the other end of the node which is right next to it also is close to 25 degrees Celsius. Have you understood this? Any doubts?
No doubt, ma'am.
Okay. If not, let's move to the next question. Just a second. So next is hyperbolic PDEs. So far what we had is this parabolic PDE. Now we'll be talking about hyperbolic PDE. Hyperbolic PDE also understand that it is transient condition. That is, it has a time term and it also has a position term. Okay. So here what happens is the condition is given to you like this. Okay. Did you notice one thing in the previous question? Here we have time and position second order. So with respect to time, you are given one condition. Okay, this is the time condition. TA equal to 25. And with respect to position, you are given two things. That is, one end of the road is 100, other end of the road is 25. Okay, so totally to solve this question, you need three conditions. One with respect to time and two with respect to position. Okay, now coming back to this question, you have first order with respect to time and first order with respect to position. So how many conditions do you need? You need one condition with respect to time. You need one condition with respect to position. That's exactly what is happening here. We have at z equal to 0. That is what? That is at the starting of the road, the initial theta value is equal to 1. Okay, so if your road is like this, what has been drawn here, and you have the intervals from, you have n intervals. So each interval is L divided by n. This is a first point to the n plus 1 point. At this first point, theta value is equal to 1. Okay, so that is given. That is the one condition given with respect to position. Now at t equal to 0, we are telling that you can assume the rest of the points to be 0. So the rest of the points, you are taking that at t equal to 0, it is 0. So that is one condition with respect to time, one condition with respect to position. So now what do we need to solve for? So this is, yeah.
Ma'am, theta is representing an angle of the rod.
No. Theta is just a variable. You can assume it to be temperature.
Okay.
It is just a variable name. Okay.
Initially, the temperature they're taking 1 then it is 0.
They are telling 1 into the road. They are keeping it as maybe 1 degree Celsius or something.
Okay.
Okay. So it could be anything. It could be temperature. It could be the volumetric flow rate through a pipe or something like that. It could be anything. Okay. So just imagine that you're starting the flow from here. At initially, no fluid is here. So you can say that the flow rate is 0. But as soon as you start the flow from here, you will have effect on the rest of the road also, right? Something like that. It could be anything. It could be flow of temperature or flow of heat or flow of some fluid, anything. It could be anything. Okay. So here, let us take temperature for our easiness, because so far we have been discussing about temperature. Now let us look what is the steady state equation. Analytically, if you are getting the steady state equation, how does it look like? Steady state means what happens? You have to take this term to be 0. So you have u dou theta by dou z is equal to minus k theta. You can bring to the other side. So you get dou theta by dou z is equal to minus k by u theta. So this is the standard equation which you can solve with your pen and paper. So when you integrate it, you will be getting theta is equal to theta in, which is a constant value, e raised to minus kz by u. Okay, so this is a standard integration procedure that we have. Now we can compare our solution to this, but before that, let's see how to solve this using method of lines. Moving forward, what you can do is, sorry. So what you can do is, here I have given some parameters. So here you have a constant u. I am taking it to be 0.5, k is equal to 1, and the length of the road is equal to 1. I am only interested in the result at t equal to 0.515. Okay, so if I am given particular intervals, what do I do in ODE solver? The t span I have to only give this. So earlier my t span was 0 to 20. So what happened in my solution, I had a value at 0, 0.1 till 20. If I'm only interested in this particular interval, what I give, my initial time is 0. And then the time intervals I'm interested in is 0.5, 1, and 5. I have to give this as my t-span. Okay, this we have already discussed while we were doing the ODE solver. So this will be my t-span. So now what you do in method of lines is, as we used to do, we'll divide the whole road into n intervals, and we'll convert this portion, okay, the position term, whatever position term earlier we had, we converted that using finite difference. Here also the position part we'll do it using finite difference. Then we'll have a set of ODE solvers which can be solved using ODE 45 or ODE 15s. So that's what we'll be looking at. So let's begin. So there are two ways in which you can solve this category of problems. That is either central differencing or backward differencing. Okay. So let us look at central differencing. So this is the equation that we have. Okay. This is the equation that we have, dou theta by dou t plus u dou theta by dou z is equal to minus k theta. This portion, that is with respect to position, I convert it into the finite difference form. So this is a central differencing equation. If you remember, theta I plus 1 minus theta I minus 1 by 2h. This is central differencing for the first derivative. Earlier we saw central differencing for the second derivative. This is central differencing for first derivative. So that's theta I plus 1 minus theta I minus 1 divided by 2h. I hope this is also clear to you. Let's put this back into the equation. So your equation is, for a particular interval, okay, so for a particular interval theta, d theta I by dt is equal to, u is a constant. Okay, now you will have d theta by dz at I, right? minus k theta. If I'm taking this to the other side, there should be a minus u. Yeah. So it will be like this. So theta, this also will have k theta I. Okay. So this portion, I'll have the finite difference equation. So finally, I'll get it like this. D theta I by dou t uh, minus u. This is the finite differencing formula. This formula, theta I plus 1 minus theta I minus 1 divided by 2h minus k theta I. Okay. Remember, for this road, you know what is the starting. Okay. Theta at the starting, that at z equal to 0, you already know, which is 1. Okay. So you only need to solve for the rest of the portion. That is from 2 to n plus 1. 1 is already known to you. So we need to only solve for 2 to n plus 1. So what happens when you are doing at n plus 1, you can write this central differencing from 2 to n. Okay. If you are writing this equation for n plus 1, what will happen? So if you are writing central difference formula for d theta by dz at n plus 1, when I is equal to n plus 1, what will happen? You will have to write theta n plus 2 minus theta n, okay, divided by 2h. But do we have this value n plus 2? We don't have this n plus 2 quantity. This is not there in our road. Our road is only till n plus 1. So what happens in the if in this method, what you'll have to do is in the last this position of the road, you will have to do a backward difference. Okay. So the backward difference, how will it be? It will be theta n plus 1 minus theta n divided by h. Okay. So from road 2 to n, you do central differencing. At the n plus 1th road, you do backward differencing. Is this clear? Why are we doing it?
Yes, ma'am.
Yeah. So first, let us look at the code for this. Give me a second. So this is your code for running your ODE equation. Okay, so these are the details that is given to me in the question. The length of the road is equal to 1. Just a second. Okay, the length of the road is equal to 1. And with respect to position, I'm dividing it into 50 intervals. Okay, 50 intervals. Now my each h will be equal to, step size will be equal to L divided by N. So my position will be going from 0 to L with a step size of h. Okay, I've discretized with respect to position. Now what happens is I need to give the initial condition. So ODE requires what all ODE requires? It requires an ODE function. It requires a t-span and it requires an initial value. Okay. T-span, as I said earlier, I'm only interested in what is the question has asked me to do. So that is from 0, 0 0.5, 1, and 5. Okay, whatever is given to me in the question. So that is my t-span. Now what happens to my y0? Y0 in the question, it has been said that at initial time, when you start the experiment at t equal to 0, at initial values are 0. So what happens? I will have all zeros. What will be the length of the initial value? Usually the y value, there are n plus 1 data points. Out of this, the first data point I already know. So I'm only interested in the rest of the n data points. So that is why I will have n zeros. See, n zeros. So my y is n zeros. Remember in our previous case, we had n minus 1. We were not interested in the first and the last. Here, we are not interested in the first alone. Last, we have to compute. That is not given to us in the question. Okay. So that is ODE. We have the ODE equation T-span and the Y0, which will be going from 2 to n plus 1. Okay. Now what will happen is I'll have to show you the ODE equation. So that is this P of R fun. Okay. So this is a function. We have the constants given to us in the question. U is equal to 0.5. K is equal to 1. The theta in, that is at the starting position, the theta is equal to 1. Why do I need it? Because when at the second point, when I is equal to 2, when I'm using the central differencing, I will require the value at I equal to 1 also. So that is why I'm giving it here. Theta in is equal to 1. And what is the length? Length is equal to, here you know, what is the length of the y here? It only takes from 2 to n plus 1. So basically, n is the length of the y. That is basically the number of intervals. You can directly take it. Length of y. L is equal to n. So the h value is equal to L by n. Now what happens? You have the theta value. So the total theta will be the y that is given to in the question, that is from 2 to n plus 1, and you also need the first value that will give you the whole theta, right? So that is why I'm writing it like this, theta in and the y that is given. Okay, so this will be your total thetas. Now my d theta I'm taking all to be zeros. There are n plus 1 zeros, but out of which I'm only interested in making equations for the 2 to n plus 1. So what happens for the 2 to n interval, I have to do the backward differencing. So that is why I'm writing it in a loop. I equal to 2 to n. This is the backward central differencing formula, sorry. Minus u theta I plus 1 minus theta I minus 1 divided by 2s. This is my central differencing formula minus k theta a. So that I'll do for 2 to n intervals. And for the last interval, that is n plus 1th point, I will be doing backward differencing. Minus u theta n plus 1 minus theta n divided by h minus k theta n plus 1. Okay. Now you have the whole d theta term. Okay. Remember the d theta will have n plus 1 entries, out of which the first entry is 0. I'm not interested in it. So what do? I write my output. I only extract the second to the last entry. Basically 2 to n plus 1 entry. Okay. So that will go as an output here. dy, I'm only extracting the 2 to the n plus 1th entry. So now going back, this has PFR fund has the ordinary differential equation from 2 to n plus 1. T span is what is given to me in the question. And y0 also, it will be all zeros for the 2 to n plus 1th point. Now I'll run this. And for plotting, what I'll do is, I'll plot with respect to position and y solve. Okay, let's see what is happening. Okay, so now I'll just show you T solve. T solve is only for 0, 0.5, 1 and 5. Let us look at y solve. Okay, y solve, if you see how many entries we'll have, n plus 1. So n is what? N is 50. Okay, out of which I'm only interested in n plus 50 entries I'll have, because basically I'll have n plus 1 entries, out of which the first entry I don't require. So basically I'll have 50. Let me see if it is 50 itself. Yeah, it is 50. Only 50 entries you have. And what is this? At t equal to 0, all my positions are starting with 0. But as time progresses, as given to me in the t solve, my y solve also changes. And you can see at different positions, it is different values. So what am I plotting? I am plotting here z versus theta. So I'll get different plots. Each plot corresponds to a particular time. So at t equal to 0, I get this violet plot here, which is monotonically, sorry, t equal to 0 is this one, sorry. At t equal to 0, you know that at all the point, the temperature, theta is equal to 0. So that is this blue line here. At t equal to 0.5, you have the red line. And t equal to 1, you have the yellow line. And t equal to 5, you have the smoothly, monotonically decreasing line. Okay, so this is how each position from 0 to 1 is the length of your road. So 0, I'm not plotting because I'm not interested in that. But here you can see that these three values are starting from 1. So basically, ideally, if you had joined this line here, you would have got the value for value at the point 0 also. So here you are getting how the road theta is behaving with respect to time and position. So now you can see this thing, this, what do you say, this oscillations in your behavior, right? This oscillations in your behavior is seen. Ideally, it is not how you get the behavior. So here, the thing is, for such kind of questions, central differencing formula, we don't prefer central differencing formula because it gives you certain oscillations. So because, and also because you know that central differencing formula you have to do to 2 to n interval, and for the last interval you have to do the backward differencing, right? So because of this mixing also, it could be a slightly unstable. So we don't prefer the central differencing formula. Rather, we prefer backward differencing. So that's what I'll be discussing like in the coming portion. Do you have any doubts?
No, ma'am.
Okay. So let's discuss what to do. If central differencing formula is unstable, what is the other method we can work with? So that is the backward difference formula. So the backward difference formula is pretty straightforward. Okay. So this portion, just a second. So this portion, now we write backward differencing formula for all intervals. Now, so that is from I to I, that is ranging from 2 to n plus 1. You can directly write backward differential formula, theta I minus theta I minus 1 divided by h. Okay, this you can use for the last interval also. There is no separate equation. So just directly put it in your equation, you'll be getting this as your ODE. Now you'll have to code this. This will be much more straightforward than your previous code. So the starting of the question remains the same. You have like length of the road is equal to 1 and the number of intervals with respect to position. I'm making it as 50 intervals. Okay. My h is equal to L divided by N. My discretization with respect to position is 0 to 0 with an interval of h till L. Now I am declaring all y to be zeros. Remember, I will have n y values. Okay. Not n plus 1. I will only have n y values. My t-span is what is given to me in the question. That is 0, 0 0.5, 1, and 5. So this is my ODE function. This is my t-span. This is my y0. All zeros. Now going back to my BFR function. PFR function, just a second. Yeah, that is this one. So PFR, first I'll write all the constants, U, K, theta in, that's the starting value. Length is directly take, if you directly take a length of y, you'll be getting n. L is equal to 1 and my h value is L divided by n. Now my whole theta will be having the first value and the 2 to n plus 1 value. So this will give me the whole theta. Okay, whole theta, I'll get it from here. Now d theta, I'm just telling it has n plus 1 zeros to begin with. Now what I do, this is the crucial part. So I'll run the loop from 2 to n plus 1. So the earlier the loop was 2 to n, then n plus 1 I wrote it separately. Here I don't have to do it. I can run the loop directly from 2 to n plus 1. So 2 to n plus 1 d theta I is equal to minus q theta I minus theta I minus 1 divided by h minus k theta I. So this is my backward differential formula. Okay. Now what I extract from the d theta, I'm only interested from the second to the last entry. Okay. So that is 2 to end. This I take it as an output. Here you can see dy is my output. Okay. So now let us go back. Let me clear everything. I'll run this. You will get this kind of a behavior. Okay. Now you can see how smoothly the behavior is. Okay. So here you can see the function that is dropping smoothly with all positions, with all time and positions. Okay. So that is why we say backward differencing is much more preferred, not the central differencing one in this case. And so now if I want to plot, this thing was there, I had here calculated with the steady state solution. I didn't discuss this. So u is equal to 0.5, k equal to 1, theta in is equal to 1. This is your steady state solution. At t equal to 0, this is your analytical solution. So let's plot this one also. This will be plotted as magenta dotted lines. Let's see the plot again. I don't know if you can see the plot. Can you see the dots, small dots? See, there are small dots. So, okay. So this t equal to 0, sorry, at t equal to 5, what happened is your system has reached the steady state. So that is why this, the steady state solution is closely matching with your t equal to 5 solution. Okay. Any doubts? Any doubts? Okay. Just a second. So next, method of lines. And today's basically what we'll be discussing is method of lines. Finite differential formula is just a bonus material that you have. You don't have to. We are not solving any problems in this thing, but it is just for your understanding. Okay. How do you solve using finite difference method? So the basic step that is involved in finite difference method is first discretize the PDE. Okay. That is, in the earlier method of lines, what happened is only with respect to position, we did the finite differencing. Okay. Temperature, the time part remained the same. The time part, dou t by dou t, this remained as such. We discretize with respect to position only. This discretization with respect to position only. But in finite difference, what happens is with respect to all the independent variables, we are discretizing it. Okay. With all this independent variable, we'll be discretizing it. That is, discretize a PDE by defining a grid in the domain of the problem with points at which solution will be approximated. Typically, a uniform grid spacing is used with H in each direction. That is, we'll have a different time. We'll have a time differencing also and also a position differencing. Now we'll approximate the derivatives using what? Using the finite difference formulas. You can use forward differencing, backward differencing, or central differencing, or even mixed differences. As we saw earlier, you can either mix backward and central difference, like you can mix however it is applicable for your problem. Now what we happen is we write discrete equations. Remember here in our case, this is also discretized and dou t by dou z. This is also discretized. Now finally, what do you get? You get a set of algebraic equations. Earlier in our previous sessions, we have said that if you have gotten a system of algebraic equation, how to solve it. Okay. So if it is not solvable, you can use like fsolve and such solvers, or if it is like linear equations, what you do? You can directly write a matrix and try to calculate the inverse of the matrix multiplied by b. Okay. If you get a system like ax is equal to b, how do you solve? X is equal to inverse of a multiplied by b. Otherwise, you can use options such as fsolve and such things. We have already discussed that. Okay. So what happens? You get the approximate derivatives using finite differencing. Rearrange it in such a way that you get a system of equations. The equations will be a system of algebraic equation which can be solved using numerical methods. Now you solve the algebraic equation using numerical methods such as direct or indirect methods. Okay. Now we'll just see what all can be done. So this is the rod conduction problem, the transient rod conduction problem. Earlier we had only discretized this portion. Now we are discretizing this T also. So for that, this is what we're doing. With respect to position, I have like 1 to n plus 1 interval. Okay. Now with respect to time, this is what I'm doing. I am discretizing time. The step size is equal to, so this I call it as I, right? So with respect to position, I'm calling the variable to be I. And with respect to time, I'm calling the variable to be K. Okay, so this is K is equal to 0. This is the same system at K equal to 1 seconds. Now I can go up to K equal to 2 seconds, K is equal to 5 seconds, like that. So these are basically snapshot of your same system taking at different time. Okay, so this is just like you take a photograph of your system. At T equal to 1, you take a photograph, and T equal to 2, you take a photograph, like that. Okay, so it's like the snapshot of a system at different time interval, K equal to 0 to K equal to whatever K you want. So how do you write it? So for writing this portion, okay, the time portion, central differencing will look like this. When you're doing central differencing with respect to time, keep Z constant. Okay, so that is if you're writing equation with respect to time, keep I constant. Okay, if you're taking with respect to I, keep K constant. Okay, now what we do is for a particular I and K, we are calculating dt. So the dt variable is what? K. So this will be the central differencing formula. You can see this Ti, but on the above, you will be seeing K plus 1 and K. Okay, so this will be the formula with respect to time. So that's what you see here. Now this we have to take with respect to position. With respect to position, what happens? We'll keep the time constant. So K is a constant. That is why you see K, K, and then you will have I taking as I plus 1, I minus 1 divided by h square. Okay, here you can see here the interval is dt, here the interval is h, minus tik, t alpha k. Here you can see with respect to position, k will remain as a constant. Okay, the same thing you can write it as, this is what? This is dou t by dou t I k. Same thing can be written as dou t by dou t I plus 1 k. So there are like a lot of possibilities. Finally, if you rearrange this equation, this is how you'll be getting. If you rearrange this equation, you keep the tik plus 1 this side and take the other things to the other side, you will be getting delta t has to be multiplied here and delta t has to be multiplied here also. And finally, you'll be, and tik going to the other side, you'll be getting tik plus alpha, this portion and this portion. Similarly, you can write this ti's for with respect to all i's and all k's. Okay, so that will be, you will be getting a set of equation. This is actually a bit time consuming for you to do this. So once you get a set of equations, you can directly solve it algebraically using the numerical methods that we have learned before. Okay, this is time consuming. And we are not asking you to do it also, but just understand this is the mathematical way of how to solve such parabolic PDEs or any other PDEs using finite differencing. Okay, any questions?
No, ma'am.
Yeah. So now let us look at the hyperbolic PDEs. Hyperbolic PDE means it is like first order with respect to both time and position. So here, what do? You apply this, okay, this dou t by dou theta dou z, this equation we have already seen. Okay, that is I with respect to position, and here we are using k with respect to time. So what happens here with respect to position, that is ui minus 1 divided by h k theta I. If you are taking both respect to position, what happens? Here what happens is you have to keep k constant, your time is constant, okay? But for this term, what will happen? You will have I constant and k will keep changing on the top. And here the time interval is theta, here the time interval is h. And you can write the whole thing. You can rearrange it in such a way that you take delta t to the other side and theta I plus ik to the other side. You'll be getting finally this equation. Okay. With whatever data you have, whatever grid points you have, you should be writing the whole set of equations, and then you can solve it algebraically. Okay. So this is for hyperbolic PDEs. Now let us look at this portion, that is elliptic PDEs. That is, it is second order with respect to both position and both time. In that condition, what do you do? Okay, so here what it is a lot of equations I know, but let's see how the method is. So what I'm doing is with respect to x, I'm telling the variable is j. The variable I'm using is j, and with respect to z, my variable is I. With respect to x, I'm dividing it into n intervals. So this is first interval, second interval, like that. So how many points I have? 1 to n plus 1 points I have with respect to x. With respect to z axis, I'm dividing it into m intervals. So how many points I have? I have 1 to m plus 1 points. Okay. So I need to write equation for this point, this point, this point, this point. Basically, all the intersection points, I should be writing the algebraic equation and trying to solve it. Okay. All this intersection point, we have to write the equation. Okay. Now, let us write. Just a second. Yeah. So now, as I said earlier, when you're writing with respect to x, what happens? You have to keep the other variable constant. So when your x variable is j, right? So you have to keep I constant. So this you can see, I is kept as a constant, j plus 1, I is constant, j, I, j minus 1. So this is with respect to x. And your time, the h difference, I'm calling this difference to be hx, and this difference to be hz. Okay, so that is hx square, and this is with respect to z. So what happens? I keep this variable j constant. So that is I plus 1 comma j, I, j, I minus comma j. And this is the difference with respect to z, hz square. So this will be my equation. This equation has to be written for all these points, all the midpoints, even this points you'll have to see. Okay, and in the question it will be given to you that this end of the road will be having one condition, that is this point's temperature might be given to you. Even this point's temperature might be given to you. Then what do? You use this equation. Using backward difference or something, you can find this. Using this portion, you can find this. So it will be like that, okay? You'll be finding this line, and using this, you'll be trying to find this line and this line. It will go like that, okay? With whatever information you have, you should be putting the information back into the equation, and you will be getting some unknown variables and some unknown equations and some algebraic equations, and you will be able to find the solution. Depending upon the information you have, there might be unique solution or there might be multiple possibilities also. So any questions? Yeah. So let us look at some problems. I'll give you some time. So today we have like ample time to solve the questions. So what I want you to do is go back to your Matlab, try to solve this and let me know the answers. We'll discuss the answers after some time. So this is the first question. All the questions today are about method of lines only. We're not solving anything with respect to finite differencing. So this is the method of lines first question. If you want any information apart from this, just let me know. Okay. So your time starts now. Once you've got the answer, please put it in the chat box also.